Good morning, everyone. Good morning, everyone.
Good morning.
On behalf of Professor Rohit Mehra and Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, I welcome you to this day 5 of this GIAN course. Today, the first talk will be delivered by Professor Rohit Mehra, sir, and then there will be a demonstration of LED fluorimeter followed by a test. So, without any further delay, I invite Professor Rohit Mehra, sir, to deliver his lecture.
Thank you, Abhishek. And I once again welcome all the participants for this final day of the GIAN program. And I hope that during the tenure of last 4 days, you might have learned so many different things regarding the assessment of natural radioactivity in air, water, and soil. So, in most of the lectures, Dr. Tokonami has tried to cover the radon and thoron components, and he has given you some idea about the diffusion factors also, and also the things related to the developments or work done by the Hirosaki universities, especially in the area of environmental radiation monitoring when the Fukushima accident was there. So he was very much active in that study also, that after the Fukushima blast, what are the increased level of natural radioactivity in the environment, or some artificial radioactivity exposures due to the leakage of some sources. Like we were discussing even a day before yesterday when I was discussing something about the fly ash. Still, so far as our opinion is concerned, the thermal, maybe it's a problem with India that to serve our energy needs, we have to be dependent upon thermal as well as hydroelectricity. But still, the nuclear is the best solution. And if you talk in terms of the problems related to the nuclear or any precautions related to the nuclear plants, in the history you can find only two accidents. One was the Chernobyl, which is presently in Ukraine, but previously at that time was in Russia. And another was the Fukushima. And Fukushima is basically not a natural accident, it was due to the tsunami. And today we will be summarizing what we have studied during last 4 days, and we'll be telling you that what are the basic recent developments for the assessment of natural radioactivity in air as well as in water as well as in soil. So most of the slides will be repetitive in nature. The reason is we have discussed those things in details during different lectures, and now we are summarizing what we have done. And during this last presentation for the day or for the course, I will be giving you what India has done for the development of the detectors, how we have contributed for the development of indigenous detectors at India itself. So I will be discussing only those detectors which have been developed by the BRC people, especially with the help of our some groups which were given some projects at that time at the initial stage to do some calibration activities, to do some uh, activities related to the authentication of the detector's results. So my students have also worked in this area, and they have done a lot of activities for the calibration, which I will be discussing today itself. That sometimes a very small thing which we say is a calibration we have achieved is we have to place a absorber of say 37 micrometer detector, but it is very difficult to achieve this value, and even a total PhD could be contributed to achieve a particular value. So I will be discussing or summarizing those things also. Another thing which Abhishek has already told you, that after this talk, we will be having a hands-on training for the assessment of uranium contamination in water samples. So I request Abhishek, Aarti, and Neha to be ready with those buffer solutions, or tell them also that how those buffer solutions are being prepared and how you just calibrate your instrument, and then final go for readings. Is it clear, Abhishek? So they will be they will be preparing the buffer solutions, and they will be giving you hands-on training related to those measurements of uranium contamination in water samples. And after that, there will be a test which will be posted on the Google Classroom, and you will be given 1 hour to solve that test, and finally you have to submit that test. And we will be sending you some performas also related to the feedback, because it is a mandatory requirement from the GIAN that the participants' feedback is to be taken. So I request all the participants to complete all the formalities within a day maximum, so that we could compile all the things and issue you certificate as early as possible by taking the permission from the GIAN coordinators after submission of some reports or attendance reports to them, and even your results to them. So today I will be discussing the summarization of what we have already shared during this last 4 days, and I will be telling you that how this uh, things have been combined together, and finally how some recent developments has led to some techniques or estimations, which now India is in a very progressive state. Means these detectors which have been developed by the Indian counterparts, when we were using some foreign detectors, so they were very costly also. So the cost has been reduced to a very low value, and the second thing, efficiency is very good enough. So I will be discussing some recent developments. Of course, this is again a very common slide which generally I used to tell my students, or even some audience when I go, that you need not to worry about radiation. Radiation is not a new thing. It was there since the beginning of Mother Earth. And now, like, what we are focusing, or how we are discussing about the natural radiations, most of the times Dr. Tokonami has expressed his views that we should measure radon, thoron, actinium, and they are the naturally occurring radionuclides which are present or which are available in the environment from the nuclear decay series, either through the uranium series or through the thorium series. And just to remember, one thing is very important. Like, you should know the basic half-lives, the basic outputs of alpha, beta, and gammas, or energies of alpha, beta, of gammas, especially on which radionuclides you are working. So, like in case of radon, the half-life is approximately 3.8 or 3.7 days. So, it is a decay chain of uranium 238, and basically it is the progeny of radium 226. So once the alpha is emitted from radium 226, we get a radon. Similarly, the thoron is again an isotope of a radon, which is coming from the thorium decay series. So after some alpha emissions, when the thoron occurs, so both the radon and thorons are gaseous in nature. So suppose there is a contamination in the soil, there is a contamination in the building material, there is a contamination in some naturally occurring substance. But once the decay products become a gaseous, so it is very difficult to control it. So that is why their studies are very important. And previously, what we were doing, that we were estimating the radon values in such a fashion that we were not differentiating their daughter products, because once the radon further decays to generate polonium 218 and polonium 214. So again, thoron further decays to give a polonium 212 and 216. So what we were doing in the previous studies, 3 or 4 year or 5 years back, we were just combining all these doses, all these effects in a single parameter, and we were saying it is the effect of radon. But now, with the recent developments or with the recent studies, we have separated the parent from the progeny, that is the daughter products. So now it is very important that whether these contributions are to the parent's contribution or is a combined contribution or is a progeny's contribution. So previously we were not having techniques to separate those progenies from the parent, but now we have developed those techniques. I have already discussed some pinhole cup dosimeters, but we will be summarizing it. So because more than 90% of the contribution is due to the progeny itself. So which we were saying actually basically the contribution of the parent, but it is due to the contribution of the daughter products. So it is very important to understand it by the persons who are working in this area. Now, if you see, you have been exposed by different methods. So you have been exposed by different methods means if you are residing in a house, like there is a building which has been shown to you. So from the building materials, from the soil, from the food you take, from the water you take, so every path is available for the exposure of natural radioactivity to you. So because radon is in a gaseous state, so once we say it is a gaseous state, so radon decays to generate polonium, and polonium emits an alpha particle which is capable to give damage to my internal linings of lungs. So I generally used to say, not in a real sense, but just for a joke sense. So the more you breathe, the more you will inhale. So the more you will inhale, the more radon will enter to your lungs. So like Baba Ramdev is saying, so you have to do Kapalbhati. So you do more Kapalbhati, more radon will enter to your lungs. So if it is a contaminated area, that is why it's a thing for a, not a real sense, but just for a joke apart. The more you will inhale, the more radon will enter, the more polonium will be released within the internal linings of your lung. And if the contamination level is little bit higher, so more alpha particles will be available for producing the ionization effect on the internal linings of your lungs. So once those internal linings of your lungs are being affected by the ionization process of the alpha particles emitted by the polonium, so those alphas are very much capable for damaging some of the internal linings and changing the blood chemistry also. So that is why after the cigarette smoking, the radon is the major cause of lung cancer. So it is very important to study this radon contamination in environment. In European countries, even in Japan, it is mandatory that while we go for construction of houses, it is mandatory for them that they have to give a certificate that this much of exposure, especially in Germany, if you say that this much of exposure is there of radon in the building. So on that day, on my previous lecture, I have discussed the basic action level for as per as the WHO guidelines are concerned for the radon in the building materials is 100 to 300 becquerel per meter cube. Now 100 to 300 becquerel per meter cube means 100 is the action level for the new constructions and 300 is the action level for the old constructions. The reason for the difference is in the new building materials, it is within your hands to have a choice of new type of building materials while you design a new building or while you construct a new building. The choice is within your hand, and that you can choose a particular building material and you can play with the ventilation conditions also. You could have a very good ventilation conditions. So that is why the action level is around 100. But in the old buildings, as there is a very little choice to do some constructional changes, especially changes related to the building materials as well as the ventilation conditions. So the action level has been recommended to 300. So that is why, what is the reason? Sometimes it is being confused by some of the researchers that it is from 100 to 300, and if it is beyond 300, it will be dangerous. It is not dangerous. It will add upon the exposure. It will have more exposure of natural radioactivity to the human populations who are residing in those buildings which are having more radiation exposure in terms of radon, that is more than 300 becquerel per meter cube. And one thing is very important. Now there is another branch of science who are dealing with the treatment of some of the you could say diseases with the high background radiation areas, or by placing the persons in the caves which are having high contamination level of radon. So sometimes due to these high contamination of radon, some of the diseases, some of the tissues are being killed, and then some of the diseases are being cured. So that is a radon bionology. There is another field where people are working. Of course, we are not working in those areas. Now, if you see this figure, that is the transportation of radon from soil to environment. I have shown one on the left hand side. There is a soil or a building material, you could say a plastered wall or a ground containing the soil or different building materials. So once the radon comes out of these pore spaces, it is called the emanation. So emanation occurs when the radon from the grain spaces or the pore spaces comes out, and once at the interface it enters to the environment, either due to the transportation, due to diffusion or convection mode, and it enters into the air in the dwellings or in the houses, either from the building material or from the soil. So we call it as exhalation. So we can perform emanation studies also, that is within the soil or within the building materials. We can perform exhalation studies also. So yesterday or day before yesterday rather, I was discussing that you can go for two types of exhalation studies, mass exhalation or surface exhalation. Generally, surface exhalation, I am not so much in favor. The reason is because surface to surface, it is different. Because your room surface will be different, my room surface will be different, and another person's room surface will be different. So similarly, depending upon the same level of concentration of radon within the same quantity of soil, if it is surface wise distributed differently, it will give a different results. But mass exhalation studies are very important, because then we could say that this much of gram of soil contains this much of radon. So that is also very important. Though it doesn't mean you shouldn't go for surface analysis. You should go for surface analysis, because you could design your buildings in such a fashion that it should have a spread of this much of a surface. But that is not very much controllable. So that is why mass exhalation is the most important term where we are focusing. Now, there are some another things which you should consider while going for different types of measurement techniques as a researcher, that you should have an idea whether I should go for a short-term measurement or whether I should go for a long-term measurement. Like the short-term measurement means you can use some active detectors to go for the measurements at some particular places and do the analysis, and the results are available within hours or within very few days. But for long-term measurements, it could take years, or even you have to divide years into several months by placing your detectors during different seasons, and you could have a proper idea that what type of contamination is available in that particular dwelling or a house or a area where you have done continuous monitoring for say 1 year, including all the seasons. So the choice is within your hand. The short-term measurements are more informative in such a fashion where some high background radiation areas are there. So with the short-term measurements by even gamma ray scintillometer, you could take within your hand and you could do some measurements. And if your gamma activities are high, you could say some high background radiations are there. Then after selecting some high background radiation areas, we prefer to go for long-term measurements to have a proper knowledge of different seasonal effects, temperature effects, relative humidity effects, even ventilation conditions effects. So while you place your detectors in any dwelling during the long-term measurements, you have to be very careful that you should note down the relative humidity continuously, you should note down the temperature, you should note down the ventilation condition, you should note down the type of building materials which people are using. So everything has a different role to play. Now short term measurements has, like we were discussing, have some advantage. It give me a quick results and immediately for some high radiation areas I could get the results. But the drawbacks are also there, that the measurement is affected by the seasonal or a diurnal variation in radon concentration. So you cannot have an idea that during summers what will be the value, during winters what will be the value. So it gives you it fails to give you the true average value of radon concentration, which is actually required for the dose calculations. So that is a major drawback with the short-term measurements. Now, long-term measurements, once you go, nowadays we are doing long-term measurements with very indigenously developed detectors, which we call as a pinhole cup dosimeters. But previously, within the solid-state nuclear track detector techniques, we were using some detectors in the bare mode. Then we developed in some cup mode, then twin cup dosimeters were developed. Of course, these are literatures which is available, so I need not to go into detail of those modes. But previously we were using the bare modes, we were using the cup modes, we were using the twin cup dosimeters. And for active monitoring, the most important still from our point of view or our research, what we have done, we still prefer these two detectors, that is AlphaGuard and RAD7 for active monitoring. And now AlphaGuard and RAD7, they are very costly because the technique is very simple, but there are only single manufacturers available worldwide. So they have a proprietary of their items and they sell their detectors at a very high cost. So now the BRC people have indigenously developed some monitor, which we call as a Radon Dew. So I will be telling you that again, it is a development in that stage where we in India has developed some of the detectors which are not only cheaper but giving you very accurate results of similar efficiency parameters. So this is the pinhole cup dosimeters and DRPS or DTPS, which are nowadays have been developed. The detailed applications I have already discussed while I was telling you regarding the different techniques for the measurement of environmental radioactivity. But just to recapitulate for some of the persons who have skipped that lecture, this pinhole cup detector, I would request Abhishek and Aarti, if they are present right now, that they could show you the detector also, how it is being opened. So they will tell you that how this is actually the photograph of the detector, and this is actually where we have placed the detectors. And day before yesterday we were discussing some Bragg's law parameter also, where we were saying that after say 4 or 5 centimeter the effect of alpha goes out or a beta goes out. So that is why they have been hanged a little bit away from the wall and from the downward from the ceiling, so that only the air surrounding the detector can affect this detector, not the building materials. So it was having some 2 compartments where one detector is placed in the lower bottom of the first compartment, and then the second compartment. And once the gas enter from the lower side, this is a mesh which is available. So it is a shape like this. So once the gas enters, it has both the radon and the thoron contribution, but radon is little bit having more high half-life, and thoron is very volatile, so it cannot penetrate through these holes, four holes which have been provided within the first compartment. Only radon could enter through these holes and could enter to the second compartment. So in the first compartment, we measure radon plus thoron contribution. In the second compartment, we measure only the radon contribution, and then we differentiate or give the difference of the measurements, and we say that this much of contribution is due to the thoron only. Because thoron otherwise is very difficult to measure if you don't have a very sensitive electronic detectors. So that is why it is even while we perform some of the experiments in the thoron for active detectors, it is generally recommended that you should place your detector very close to the points where you could feel that from the soil the thoron could enter into the room. Like you have to place your detectors very close to the floors or the floor and the wall alignments. You have to place your detector very close to them. Now, again, this which I was discussing before the start of this lecture, that sometimes it seems very easy that we were doing some calculations based upon the measurement of progeny, that is due to the polonium, which we call as a DRPS, direct drawn progeny sensor, that we are having a alpha particle of the order of 7.69 MeV, which is coming out of the polonium 214, and we want to measure this polonium with the help of our LR115, which is sensitive for the energy range of the order of 5 MeV or 4.5 MeV, 4.7 MeV. Now, to make this alpha coming out of the polonium 7.69 MeV sensitive to our detector, that is of the order of 4.7 to 5 MeV, we have to place an absorber. And for the standard process nowadays is alumina is mylar. It's a type of aluminum film which generally we use as a wrapping paper. It's a similar type of it, but it is a little bit more, you could say, pure or developed in such a fashion that it is having a pure aluminum. And then this mylar film of thickness 37 micrometer was used in case of DRPS, where the alpha of the order of 7.69 MeV was absorbed, and then it was allowed to fall on the LR115, so that it comes into the sensitivity range of LR115. Now, to come out with this 37 micrometers, so many people were involved, and our group was working in collaboration with the BRC people, where to come out with 37 micrometer and 50 micrometer in case of DPPS, that is direct thrown progeny sensor, where we are measuring a alpha particle coming out of polonium 212, that is of the energy range of around 8.7 or 8.9 MeV. So we have to use a 50 micrometer. Now, commercially, the problem was, if you go for a purchase of mylar film, so mylar is available in a commercial size of 25 micrometer. So it was very difficult to cut this 25 micrometer into half and make a second layer of 12 micrometer. We could place over 25 micrometer and make it 37. For 50, it was not a problem. You could use two layers simultaneously together. 25 plus 25 will give you the 50 micrometer thickness. But for a 37 micrometer, it was again a problem. So once we were working with the BRC people and once we were working with their team, so we found that it is very difficult to get a 12 micrometer thick aluminized mylar so that we can make our detector of absorber of thickness 37 micrometer. We discussed with the suppliers also, and they said commercially it is not possible to prepare a 37 micrometer because the order size is very less. So if the order size is in bulk, so we could always go for 37, but as you require only for research purposes, otherwise the company was not ready to give. So what we tried with different materials of 10 micrometer thickness who were having same absorption parameters equivalent to the mylar, so that we can place a 12 micrometer absorber over this 25 micrometer aluminized mylar, and absorption parameters are similar, so that we could come to a sensitivity range of LR115. And then, to our surprise, the LR115 is basically a cellulose plastic track detector, cellulose nitrate, which is having a thin peel of film of around 12 micrometer over the plastic sheet to provide its strength. So that 12 micrometer sheet is having similar absorption parameters as compared to the aluminized mylar. So then finally we come to a result that we could take one aluminum film of 25 micrometer and then peeled off detector film of 12 micrometer, which will not act as a detector but will act as an absorber. So we place it over that particular 25 micrometer mylar and make it as a 37 and then go for the measurements. So you could see that while reaching to a very small value, that is 37, a lot of efforts were being put, because every time we have to do the calibration whether the absorption capacity is similar or not. We have tried with different materials, but finally we came to a conclusions with the that this 12 micrometer upper peel off layer, we just peel off the detector and use that 12 micrometer layer over the aluminous mylar to make it 37. So this is actually the size or detectors which you could see from this. This is a 12 micrometer is a cellulose nitrate which we place over our detector. Now this cellulose nitrate is not basically used as a detector but as an absorber, and then again a aluminous mylar, and then the deposition occur. So this is 37 and this is 50, means you can place two layers of 25 micrometer over it. And these are the sizes, basically give you just an idea that this much is the length, that is 4.1 centimeter. It is thick, and diameter is approximately 6.2 centimeter. So this is just giving you an idea, this picture, that how the detector is placed, what is the size. Then we generally place all three dosimeters together and finally calculate the results, which we have already discussed. Then we could skip this slide, and protocols, again I could repeat that generally it is preferred to go for 3 to 4 months of measurement with a single detector placed for a particular season, and then repeat the process for the next season, and again repeat the process for the next season, and finally cover whole of the year in such a fashion that you get a total annual concentration. And then after removal, generally it is recommended to have a chemical etching of these detector. The reason is otherwise detector will be sensitive. So you do the chemical etching, you develop those films, and finally after chemical etching, those films are now good enough that they will not be affected further by the natural environmental radioactivity present in the air, and you could count at any time. So generally the chemical etching process is done with the help of sodium hydroxide 2.5 normal, and sometimes it is also very important. Some of the students doesn't know that how to make a 2.5 normal sodium hydroxide solution. So as a student, as a physics or a chemistry student, you should know sodium is 23, oxygen is 16, hydrogen is 1. So 23 plus 16 plus 1 gives you 40. So if you make 40 multiplied with 2.5, you get 100. So means 100 grams of sodium hydroxide pellets have to be mixed with 1 liter of water to make a 2.5 normal solution. So I think you got an idea that how to make 2.5 normal. So atomic weight of sodium hydroxide is 40. So you make multiply 40 with the normality, that is 2.5, means 100 grams of sodium hydroxide in 1 liter of water will give you 2.5 normal sodium hydroxide solution. And if you want to take 250 milliliter of water, so you could take 25 grams. If you want to take half a liter of water, you could take 500 gram or 50 grams. So that you could always calculate. Then with the help of spark counter, we calculate, and finally we calculate the doses. Now, protocols which everyone should remember, like once I have already discussed, that the deposition surface of aluminized mylar should face the indoor environment. Means it should not be on the downward side. So it should always face the external portion. And second thing is you should have a proper record of the ventilation conditions, and it should be placed away from air conditioner, vents, or doors or windows, so that every time once the door is being opened, some external exposure is there, or some indoor air goes out. So you should always place them away from ventilators or air conditioning vents or fans. And second important parameter is you should keep them away at least 20 centimeter away from the wall and the roof, so that the direct building material could not give the interference. And another, we have already discussed that the reactor could be exposed for 3 months, 4 months, 5 months, 6 months. It depends, because some of the regions are like, if you want to place your detector in the Ladakh region, sometimes for 6 months you can't go there. So you could place those detectors for 2 seasons only. So that is the choice of the area also, that is the availability of your dwellings or the areas also. And retrieval rate is very less also. And sometimes once we hang our detectors, and the people after few days or sometimes they throw away our detectors, because they also have a fear factor, because it is very difficult to do these type of activities, especially in the country like India, where the people are not so much educated that you can make them aware, because they are very afraid of that what we have placed in their houses, and whether we have placed some cameras or whether we are monitoring something else. So it is very difficult to convince the people. So generally, while placing our detectors, again, no doubt it is not a part of our discussion, but as a PhD supervisors, we have to tell our students that how to go to the particular areas, how to take the help of local administration, how to take the help of the panchayats, how to take the help of different knowledgeable persons or educated persons of those areas, so that they could convince the people of their particular area. Because sometimes if I am from some particular region and I am going to place my detector in Ladakh region, so they will not understand my language, they could understand only the language of a local person, and then that local person is capable enough to convince them that this detector is not a problem for them. So it is very difficult. So though it is not a part of any protocol, but as a researcher, as our experience says, our retrieval rate is not more than 70%. Nearly 30% of the detectors, they get either damaged, or the residents place them at their different places. So it is always recommended that you place 4 or 5 detectors in a particular dwellings, so that you could have at least good retrieval or a good retrieval of that particular region. Then, of course, quality assurance and decay product measurements are also very important. Like, you have to go for the appropriate sensitivity factors. Like previously, when we were using the bare mode techniques, we were using a sensitivity factor of, say, if after retrieval we get 1 track per centimeter square per day. So we say it is 50 becquerel per meter cube. Now the sensitivity parameters have changed. So this was a general sensitivity parameter. Like, if you are getting 1 track is basically the effect of the damage caused by the alpha particle on our LR115. So if we were having 1 track per centimeter square per day, we generally call it as a 50 becquerel per meter cube. The reason for that particular factor was because at that time we were not sure that whether it is a contribution of the progeny or whether it is a contribution of the parent, radon or the polonium. But now we have used some different sensitivity factors. This is what we have mentioned also. So you have to, in my previous lecture, I have mentioned some sensitivity factors also. So you have to understand what type of sensitivity factors you are using. And then for background measurement, at least you should place 10 to 20 detectors, so that you could always remove the background from the actual measurement. So that is also important. And then this is another very big jump or a leap in the development of this radon due portable radon meter, which is giving lot of competition nowadays to Red 7 and AlphaGuard, which was approximately costing around 15 to 20 lakhs AlphaGuard and around 8 lakhs Red 7. So this portable radon meter is approximately costing you around 1.5 lakhs. So which has been indigenously developed by the BRC people, and this is a similar type of a detector where we are using the scintillations and the counts, which I have already discussed in my previous lecture, that we were doing some measurements based upon this radon due. And the algorithm has been developed by the in-house by the BRC people. And this is actually how it is set up or working. There is this is a water sampler. You can bubble it. Means bubbling means you within the bubbler you could generate the radon within the water, and bubbles are generated. From the bubbles the radon will enter, and once it enters to this, there is a pump inlet. So once it enters this, there are detector assemblies which are placed here, and then finally you are getting the signals. So radon in the setup incubating detector volume was flushed out for 5 minutes if you want to measure in water. So then the pump was kept again for 5 minutes so that the dissolved radon get transferred to the detector itself. And it was operated for nearly 15 minutes to 1 hour, and then you get the final results. So there was also a radon due meter. You could use it for a soil also, but for a soil, I think there are some mismatch in the this slides. Just yeah. There is just a minute. Just a minute. Display is not good enough. Yeah. Of course. Now, to deploy the radon due for the soil measurements, so you have to measure the soil gas concentration with the help of the probe given with the radon, and you have to hammer that probe head into the depth in the soil itself. So if the probe encounters surface resistance, a rock may be encountered. In this case, modify the insertion sites. Means ultimately the probe should enter into the soil. Then remove the probe head and the pipe once the probe has been placed at a desired depth, replacing the probe head with the sample head connected to the inner sampling pipe is a good idea. And finally, then if you have inserted the probe, you have to go for the measurement. Again, the similar type of protocols, like you have to start the pump and extract the radon from the soil itself, and then you have to repeat the process for 1 hour. So this is a protocol for the measurement of radon in soil. And then for the protocol for the measurement of mass exhalation in soil, so mass exhalation, I have already discussed that you have to take a known value of sample, and then radon due measurements included a mass exhalation chamber for measuring mass exhalation volume. So the chamber must be free from impurities and handled very carefully. The spent scintillation shell is placed with one that is maintained at 3 hours following the radon flushing to ensure that it is clear from the background. Then is smart radon due is turned on. The cycle is set to 1 hour and the pump is turned off for diffusion mode. Now we are not sucking. We are just allowing the soil to diffuse or radon to diffuse out of the soil, and the pump is turned off, and only due to the diffusion process some radon is entering into the chamber. Then another important part is, or a detector is red 7, which I was discussing, is still giving you the best accuracy. We are having this detector in our lab also. Again, it is a detector based upon the alpha emitter with spatial spectral analysis, and it works on two different modes. One of my student, Dr. Komal, has worked a lot on this detector, and Pankaj, they have worked a lot with this detector. And then these are some protocol or different ranges that you could measure the radon as well as thoron simultaneously. Again, it is a new development. Now, advanced version of this has already been produced by the Durage. So again, it could be used for a very accurate measurements, but it gives you a very instantaneous data. So either you could continuously monitor it for 2 or 3 hours, 2 or 3 months, then it will have a proper record of a particular season. So this could also be used for a measurement of radon in gas as well as in water samples. So there is a desiccant arrangement is there so that the moisture content could be removed, and alpha detectors are there, so which you could use. Again, it is a water sampler. You could place a desiccant over the water sample so that the moisture will be removed and the bubbles are being generated. So with the help of a similar type of arrangement. Then again, it is a protocol which you should remember that before starting the test, all the doors and the windows should be shut for 12 hours according to the EPA protocol, and no air exchange system or ventilation fans may be running. And make sure that air intake is at least 30 inches above the floor and away from the wall. With the laboratory drying unit used to dry the sampled air, the desiccant will have to be replaced every 7 to 14 days, because desiccant is generally used to remove the moisture content. So you have to remove it after 7 to 14 days so that you could use a new desiccant to remove the moisture content. So rising relative humidity may indicate that the desiccant is exhausted or that there is a leak in the sample path. So replace the old desiccant with the immediately with the new one. So with the time resolutions of the data provided by the RAD7, anomalies are clearly revealed. Now you could use either a sniffing mode to take the measurements, and then you could use at least 4 or 5 multi cycles readings. So if it is more than 1 hour after the sample was taken, a correction must be applied for the decay of radon in the sample. So these are few protocols while you use the RAD7 in water. So before making the measurement, the RAD7 must be free from the radon and it should be dried. RAD7 must be purged after every measurement. Purging is very important because the previous readings effects will be there. So you have to purge it again and again after performing a new. And the relative humidity must be very close to 6%. Otherwise, again, we have to repeat the purging process. So again, these type of measurements are very important for estimation of polonium-218 and 214. And this was one of the case study where we have performed some of the studies in Bathinda, Churu, Hanumangarh districts. So I will show you the results. Hanumangarh, Shri Ganganagar and Churu districts. We have performed some annual average indoor radon concentrations ranges. So it ranges from 4.5 to 99.39 becquerel per meter cube. And EEC basically is the effective equivalent radon concentration. So EEC values are being generally calculated with the help of a parameter. We could say because it is giving me the actual results related to the parent itself, not including the progeny factors. So it is nearly 2.7 to 17.6 with the average value of 8.6 becquerel per meter cube. Then again we have calculated the EEC for attached as well as unattached aerosols also, where we have placed some wire mesh over the detectors, and those values are shown in the figure. And if you talk in terms of annual average effective dose, so it ranges to 1.52 to 8.63 microsieverts per year. Inhalation dose for mouth was approximately 0 to 36.83 microsievert per year, and inhalation dose for nose was 0 to 8.57 microsieverts per year. So again, this indicates that while we breathe, we should preferably breathe from the noses, because it gives you a little bit lesser impact, because some of the radons are stick to your nostrils. Then again, correlation we try to calculate that how the radon and its progeny, they are interrelated. So we don't say that they are very much correlated, but of course R square values are a little bit sensitive in such a fashion that in all the cases the radon concentration and EEC values are not highly correlated. So daughter plays a different role. So that is why in the bare mode we were doing some confusions. We were considering all the daughter as well as the parents as a similar. Now with the advent of the technology, with the development of the detection technique, now we have to separate the main radon concentration from the effective equivalent radon concentrations. So these are the seasonal variations which we have presented for the rainy seasons, for the winter seasons, for the summer seasons. And generally in case of rainy and winter, the concentrations are little bit higher. The one factor is during the winter and the rainy seasons, we have closed environments because our ventilation conditions are poor and moisture contamination is very high. So relative humidity is very high in some of the areas where the rains are there. So then the radon or the gases get trapped with that particular high level of relative humidity. And also during the winters, the doors and the windows are being closed. So that is why the contamination is little bit on a higher side as compared to the summers. So this is a worldwide trend. So if you have better ventilation conditions, you would have lesser concentration of radon. So that is why it is always preferred to have the houses designed in such a fashion that your ventilation conditions are very good enough. So that is what I was discussing in my one of my lecture, where I was discussing that we are using now closed kitchens, closed rooms, and placing more granite in our houses. So we are being exposed to some little bit higher values with the help of these type of building materials and ventilation conditions. So it again gives you an idea about the three districts, that is the radon concentration and the radon progeny contribution. And in most of the cases in winter it is high as compared to the summer. So this is what we were discussing. Then these are the average seasonal attached or unattached fractions. Now this is a comparison of the worldwide studies, which are worldwide for different areas, for even for different regions in India, Hamirpur, high background radiation areas in Odisha, even Hanumangarh district, Shri Ganganagar district, Churu districts, we have calculated and we compared our results with some of the different radiation workers or persons who are working in this area and presented their results. Now, again, like for water sources, you could use hand pumps, you could use tap, you could use canals. So you should have an idea that what type of geology is there while you collect your samples. We generally don't prefer the tap water because tap water is basically the municipal corporation water and the source is different at particular times. Hand pump is or the canals are the best sources while you collect the water samples. And again, we found that in these three districts, we have a comparison also for infant or children or adults. We have done the calculations based upon their water intake, and we tried to calculate the doses due to the radon concentration in water. So it is only due to the radon concentration in water. So every concentration in air, water, and soil, it contributes to your natural average contribution. And along with that, radon, uranium also contributes. So which and now we will be performing one of the experiment also, that how to estimate the uranium contamination in water. So all these mixed together gives you a total annual exposure. So it is very important to have a parameters related to the air as well as to the water as well as to the soil. I don't think so that there is further needs. So thank you once again, and with this, I came to the end of my presentation. That today we are what we have discussed. We have discussed some of the basic developments of different techniques and detectors that during the tenure of last, say, 10 to 20 years, how we have changed from the different one technique to another, and what type of developments are now being done. So of course in India a lot of people are working together. The BRC is having a very solid group who is working in this area for the development of new detectors. And as an indigenously developed detectors, they are little bit having lesser cost also, but efficiencies are good enough. So with this, I finish my talk, and now I request Abhishek is there.
Yes, sir.
Yeah. So Abhishek, if any query is there, anyone want to ask, we could take that query. Otherwise, after 5 or 10 minutes, I would request you people to just make arrangements of such a tell them how to prepare the buffer solutions also. Whether you are having standards, means tell them from the very basics.
Okay,
Means
sir.
So you might have prepared some of the solutions, but at least tell them that we prepare this 10 ppb 100 ppb buffer solution so that we could do a comparison. Okay.
Yes, sir.
So with this, I thanks all the participants once again, and request you that you personally visit our institute for any type of help you require. You always contact me. You could always contact me if you require anything related to this field of environmental radioactivity. We are always there. My students are always there. And second thing is, like in future also we will be trying to organize one or two conferences in our institute where we will be bringing some of the different experts and presenting you some of the results where they are working in particular areas. So in future, I would love to invite you people to my institute to NIT Jalandhar. And with this, I thank all the participants. I request all of you to please follow the guidelines as far as the GIAN course is concerned. Your feedback is very important to get the certificate. Your test is very important. So we will give you 1 day's time to submit everything by tomorrow. So I request, one question. Karanjit, you want to ask something?
Yes, sir.
Yeah.
Actually, sir, I am from NIT Manipur. Suppose, sir, if we want to measure this, the activity levels of these natural radioactive levels from soil samples,
Yeah.
then how do we approach to you? Suppose if we want to measure.
You have to collect the soil sample as well as we have given you an idea that you should collect your soil at a depth of around say 1 meter or a 0.7 meter. Then because our detector is having a different geometry, some other agencies detector might be having a different geometry, so you could always contact us so that we can send you the exact dimensions of the geometry or the box which is available with us and which is suitable for our detector, so that you could purchase those boxes from the market, and rest of the things you could do at your own institute. Means you could sieve your samples at your own institute, you could microwave dry at your own institute, you could pack it for 3 months or 1 month to attain the equilibrium, and then you could send those samples through courier to us. We provide two types of consultancy. One as a paid consultancy, like we do the analysis based upon if some persons want to get some sample analyzed by us, so we are having instrumentation facility. Then you have to apply to the central instrumentation facility. And second is the inter-comparison or a collaborative work which we perform with our labs. So there you need not to pay anything. So we will have some joint publications. We will try to help you in publications of those results also. It is up to you that what type of collaborations you want to achieve.
Okay, sir. Okay, sir. One last question is, sir, you have mentioned about the PET. So suppose if we are choosing in the PET option, so how much per sample you charge?
So it depends upon the sample to sample actually. But generally, we prefer to go for analysis of minimum of batch of 20 samples at around 250 per sample.
Okay.
The rate list is available on our website also.
Okay.
So for uranium it is different. For radium, thorium, potassium it is a different rate. For heavy metals it is a different rate. So that is what I am saying. Now you could use any of the mode. So then you could. It's not a compulsion that every time you send a sample to us and you have to publish with us. It is not mandatory. The only thing is, if you send a sample to us and don't pay any charges, then our persons have to work over those things. So my PhD students will be working over those samples. So at least they require in return that they should be a collaborative work.
Okay. And sir, is there any option that suppose I personally come to your lab and I also work and learn?
Yeah. We are open. Even during winters and summer, some of the students from different institutes come to us. They work for say 15 days, 20 days in our lab. Recently, one student from the Central University of Haryana was with us for 21 days. So she was working with the instrumentation. So that's not a problem. The thing is, we are open to everyone. We just want to give a maximum benefits of the instrumentation facility available with us to all the human population available in our area or surrounding areas. It's not a problem.
Okay, thank you, sir. So for further,
Good morning.
I will consult my guide and I will
Yeah, sure.
approach her to you.
Sure.
Thank you, sir.
Good morning, Mehra sir.
Good morning, Prakash.
Myself Prakash from Kerala.
Yeah.
Sir, one thing. Recently, I have purchased a sodium metal detector.
Hmm.
The thing is that I have a shortage of these calibration sources: Rg, thorium, Rg, uranium, and potassium. And,
Actually,
what can I do? And as I encouraged with
one thing is there. If you have purchased it from Atomtex or some other
no, I have purchased from Nucleonics.
Nucleonics. So Nucleonics could provide you some cesium sources actually for the calibration purposes.
Yeah, but they are not providing any sources for this potassium and radium and thorium. That is
if you, it is not necessary to go for Rg, uranium, thorium, and potassium.
Oh, okay. Yeah.
If your peak is calibrated for cesium, the detector will work for all the energies. So,
is it so? Okay.
Yeah. Only thing, because Rg, uranium, thorium, potassium, actually it cannot be transported. So, lot of protocols are being involved, lot of permissions are required to send the sources. So, otherwise it is very difficult. Otherwise, I could always help you. But as it is, some legal bindings are there that we can't send it through post, we can't take it along with us. So that is why cesium is generally provided by the vendors.
Yeah, that is true, sir.
Yeah.
And I have encouraged with the IAE also, but they are not having that sources right now. Actually,
actually, if somebody will be having, they will not be providing you. Even health physics lab in IUAC is having those soil samples, but they will not be providing you because they are bound by the protocols.
Okay, that is true. Okay, and one more question, sir. Actually, I have some MSc physics students, and if they want to visit your institute and if they want to stay for 1 or 2 weeks, that would be possible, sir.
That could be possible. We could provide them the hostels depending upon the availability, but for that you have to send us an email so that I could get it confirmed from my chief warden whether hostels are available or not.
Thank you. I'll be in touch with you, sir.
Sure.
Yeah, thank you very much.
So, if there are no further queries, so I will finish my lecture here, and I once again thank all of you for giving your valuable support for making this program a success. And I hope that it might have served at least to the expectation of some of the people. There are some limitations. There might be some limitations. We are open to take suggestions from all of you, and so that we could improve in the next course. Actually, my personal feeling is that we should always go for offline modes, because then we could have one-to-one interactions. So, but due to the shortage of time period, along with the non-availability of the time schedule with Dr. Tokonami, so we cannot make it as offline. So we try to go ahead with the online mode, and luckily we got it approved. And we are thankful to the coordinator GIAN's National Coordinator GIAN for giving us an opportunity to serve some of the researchers in the area of radiation physics, to share our knowledge along with Dr. Tokonami's knowledge, so that they could it could help them to do a good type of research in this area. Thank you once again, and thanks a lot. Abhishek, you could continue after 10 minutes break, because you have to make a setup in the lab itself.
Yes, sir. Thank you very much, sir, for your detailed lecture. And dear participants, we will be joining the same Google Meet link after 15 minutes at 11:30 a.m. And we will start the demonstration of LED fluorimeter then.
Abhishek, after that, you share the feedback and that test also to them, and so that they could upload it. Okay.
Yeah, sure, sir. Sure, sir.
Okay, okay, beta. God bless. God.
Thank you, sir.
Thank you, sir.
Okay, ji. Thank you.
Thank you very much. Thank you. Have a nice day.
Thank you.